Hello everyone, my report title is Multi-UAV Cooperative Exploring for the Unknown Indoor Environment based on Dynamic Target Tracking. My name is Ning. And the content of my report is mainly divided into the following 5 parts. The first is background introduction. As for the UAVs, due to its flexibility and low-risk characteristics, UAVs have been extensively developed in exploring unknown indoor environments. Individual UAV has certain cognitive and movement limitations, but multi-type UAVs can solve many complex problems, such as ant colony algorithm finds the shortest path, or bees select food resources collectively through a wake dance. So multi-type UAVs can be used to explore unknown indoor spaces without GPS. This can provide basic environment information for search and rescue missions. For example, dangerous buildings after earthquakes, hazardous gas factories, under mines, and so on. Next is the application of path planning algorithms in robots. The core of robot exploration in unknown space is to use a suitable path planning algorithm for navigation. According to the algorithm idea, it can be divided into graph-based search algorithms and sampling-based search algorithms. According to the degree of information mastery, it can be divided into global algorithms based on a priori complete information and local algorithms based on robot sensor information. Therefore, this is a scenario description of research content. The scenario is a GPS-denied unknown indoor environment with irregular borders. And the problem is how to use multi-type UAVs to explore GPS-denied unknown environment and draw a boundary map of the entire indoor environment. In this scenario, each UAV starts from the same starting position. The first UAV uses the all-round algorithm to fly around the boundary of the environment, and the red line indicates the first UAV's flight path. When the first UAV flies low on power or stops working due to an unexpected situation, the second UAV will start to relay. In this progress, the tracking D-Starlight algorithm will be used for tracking relay, as shown in the yellow line. When tracking is completed, the second UAV will continue to fly around the boundary of environment using the all-round algorithm until it returns to the starting position. Due to the whole exploration progress, the path of UAVs around the boundary of environment is drawn in real time, and the boundary of the entire map is drawn when the exploration is completed. The second part is related works. First is bug algorithms. It was proposed in 1986 and developed a series of versions of the bug algorithms. The basic idea of the bug algorithms is make the robot move towards the target. If the robot encounters an obstacle, it will first move around the obstacle and leave it, then continue to drive towards the target. And bug algorithms can be divided into angle bugs, M-line bugs, and range bugs. For the field of indoor exploration, A minimizing navigation method named Swarm Gradient Bug Algorithm, SGBA for short, for tiny flying robot to explore the unknown environment is proposed in 2019. Following is the main steps of SGBA. First, each robot moves in a priority direction called outbound travel. Secondly, use following when robot encounters obstacles, and if there are no obstacles, move in the direction of priority. Thirdly, the robot will back to the original location with 60% battery remaining. This progress called inbound travel, but the SGBA still has some shortcuts. For example, different robots may repeatedly search the same area, and a single robot cannot search at the maximum range and energy constraints. The D-Starlight algorithm proposed in 2002 is a lightweight version based on the D-Star algorithm, suitable for planning a path to a target point in an unknown environment. The main idea of this algorithm is assuming that the unknown areas are all free spaces. The path planning is implemented incrementally, and the shortest distance from the target point to each vertex is found by minimizing the RHS value. Incremental AIRC star is an enhanced version of anytime repairing A star, which mainly realizes the process of continuously replanning the path and pursuing between the tracker and the tracked in a dynamic environment. On the basis of AIRC star, the starting point and target point are constantly changing, and each time the planning will update the state of all expanded vertices, update the widget, and planning a new path. In summary, there are two main algorithms proposed in this paper: Wall-Round and T-Tracking D-Starlight. Wall-Round navigates the target around the wall based on the bug algorithm of capturing the target point. Tracking D-Starlight combines the increment AIRC star algorithm with the D-Star algorithm to design an algorithm that can continuously replan and track the dynamic target in an unknown space for relay tracking between UAVs. The third part is method. I will introduce the above two algorithms in detail. First is wall-round. For the traditional bug algorithm, the robot keeps moving towards the target point. When encountering obstacles, the robot will be kept close to the target point to avoid obstacles by surrounding the obstacles. Compared with the bug algorithms, the wall-round algorithm doesn't need the target point. The robot only needs to cycle around the map boundary and finally return to the start point. Here is the main idea of wall-round. This algorithm divided the whole unknown space into 4 directions: front, back, left, and right. These 4 directions are fixed, but in the case of the UAV, it needs to keep choosing the correct directions to fly around the wall. Therefore, the UAV itself has state quantities in 4 directions, including main direction, next direction, previous direction, and opposite direction. main direction is the most important, indicating the direction of the current UAV pointing to the wall. The other three directions are calculated by rotating clockwise according to the main direction. For example, when main direction points to the right, next direction points to the back. Previous direction points to the front, and opposite direction points to the left. By analogy, 4 directions can be calculated at any time. Following is the main idea of tracking this starlight. The algorithm retains the calculation method of the priority queue in the D-starlight algorithm. Firstly, the RHS value is calculated by the formula 1 using the G value, and then the key value of the priority queue is calculated using the formula 2 and arranged in lexicographical order. On the other hand, on the basis of the D-starlight algorithm, the data structure of the delete queue in the AIRC star algorithm is added to store the vertices in the search tree that do not belong to the root vertex of the search starting point during this search. Here is an example of tracking this starlight. There is a 5 multi-3 grid map. The position of the robot start robot at B1 and go at D3. Left graph is the real environment of the entire map. The robot can sense a map of a unit distance around. Heuristics is the heuristic value of the robot that at the reachable grid point, and the heuristic function is the Manhattan function. Frontier contains vertices that have been expanded. Delete contains vertices that have been deleted. Km represents the heuristic compensation value after the start of each move in order to maintain the strict ascending order of the key value in subsequent searches. As shown in figures, the yellow grid represents the vertex in the priority queue. The red box vertex represents the vertex to be expanded at next time. The arrow between the vertices indicates that the parent vertex points to the child vertex, and every vertex has a G value in the upper left corner of the grid, RHS value in the upper right corner of the grid, and a key value below in the grid if it exists. The first search progress is expanded from the goal in the initialization. The RHS value of the goal is set to infinity and 0 according to this formula, and the priority key value of the vertex is calculated according to this formula. In the example of this algorithm, the 4 connection expansion method is used. By selecting the vertex with the highest priority in the priority queue, the neighbor of the vertex are expanded and put into frontier. From initialization to step 7 represent the process of starlight in the first expansion process. The Finally, get the path pointed to by first path. And at the end of the first search progress, we get the first path, and the frontier contains this vertex. And also, this is a search tree. Search tree start from D3. Update robot location and map information. Goal moves to C3 and robot moves to C1. In this progress, we need to cut the search tree and need to keep the search subtree with C3 as a root vertex. And for all delete vertexes, if its neighbor vertexes belong to the current search tree, not the vertexes in the frontier. The vertex is re-expanded and added to the frontier. Similar to the first search, calculate the shortest path from C1 to, and here is the second path we get. Last is a diagram of system algorithm framework. Fourth part is experiments. First is a comparative experiment of tracking the starlight algorithm. The purpose of this experiment is to verify the performance of the tracking the starlight, which mainly compares the 4 indicators of the tracking time, the tracking moving distance, the number of expansion, and the success rating. The experiment compares the tracking the starlight algorithm with repeated D-star algorithm. We can see from the table that tracking the starlight is better than repeated starlight in the above 4 aspects. Next is the simulation experiment. The purpose of a simulation experiment is to verify the rationality of the method of cooperative exploring for multi-UAV in an unknown indoor environment based on dynamic target tracking. The content of the experiment is to build a simulated indoor environment. 6 quadrilateral UAV models use the method proposed in this paper to explore the entire environment and draw a boundary contour map. This is the final simulation experiment result. Last is the conclusion. In summary, the main contribution of this paper first is proposed the well-rounded algorithm for flying around the boundary of environments. Second is proposed a dynamic target tracking algorithm for relay between multi-type UAVs in unknown terrain. Third is built a multi-UAVs exploration system that can navigate autonomously in an unknown indoor environment. In conclusion, in order to improve the efficacy of indoor exploration in a GPS-denied environment, this paper proposes a multi-UAV collaboration exploration method based on dynamic target tracking. This method takes advantages of the well-rounded algorithm and the tracking the starlight algorithm, using the well-rounded algorithm to explore the boundary of the unknown indoor environment, and uses the tracking the starlight algorithm to collaborate among UAVs. Finally, completing the task of exploring the entire unknown indoor environment. The method processed in this paper can effectively tracking the moving target in unknown terrain and can achieve good results in simulation experiments. Thanks for your listening.